Oh, can I share the screen, my screen?
No, I can see your screen.
Okay, I will start screen sharing.
Okay, I see you. I see your screen.
What this is
Kazuya, Matsumoto, are you ready?
I changed the monitor setting now also. So now okay.
Okay. If you are ready, I'm presenting your presentation, and we start the session. If you're ready.
I'm ready.
Good morning to everyone. You are welcome to Malaga, to the International Conference on Computation Science and its Application. I'm Luigi Santopietro, and I'm the chair of the session. And we start with the first presentation, high-performance software systolic array computing of multi-channel convolution on a GPU of Kazuya Matsumoto, Yoichi Tomioka, and Stanislav Sedukin. And Kazuya, the stage is yours.
Okay, thank you for your kind introduction. I'm Kazuya Matsumoto from the University of Aizu, Japan. I'd like to start my presentation titled High Performance Stochastic Array Computing of Multi-Channel Convolution on a GPU. Screen is okay.
Okay.
As you may know, the convolution neural networks are an effective approach in machine learning to solve many kinds of real-world problems. And convolution neural networks consist of several layers, including convolution layers, activation layers, and fully connected layers. In particular, the convolution layers are the most compute-intensive part in the advanced CNN models. And in this study, we only deal with convolution layers. And the convolution computation can be implemented in different ways, such as by utilizing K-means matrix multiplication, K-means routines, or Venn-Graph algorithm, and fast Fourier transform, and also direct computing for convolution is possible. And but in this study, we have implemented a convolution over a method over stochastic array-based direct computing with multi-channels on a GPU. And we have designed two different methods, and we evaluate the methods of implementation on the GPU, on the NVIDIA desktop GPU of the Ampere architecture. And note that our implementation in single precision and 32-bit numbers, and this GPU has tensor cores, but we don't use that, and we only use CUDA cores. And this research is based on the existing previous research and proposed in the previous paper. And they demonstrated they propose a stochastic array-based model-based direct computing, and their implementation can achieve a higher performance than deep learning libraries such as cuDNN and cuArrayFire on a single GPU. But their implementation is to verify the effectiveness of their model, so their implementation is not targeted for real application for the CNN models, but so their implementation computes a 2D convolution of a single input and a single output channels, SISO channels. So to accelerate the deep learning further, and we did an extension of the SSM-based approach for convolution of multi-input, multi-output channels. And this shows the formulas of the convolution computing. And upper one is a 2D convolution, and the lower one is a multi-channel convolution with C input and K output channels. And in the 2D convolution, that the H by W image and a single image and a single filter, M by N filter, is computed for single output, but for multi-channel convolution, that the multiple inputs and the multiple filters, and also the outputs are multiple. In this figure, there's only one output, but the multiple outputs are supposed to be considered in multi-channel convolution. And this 2D convolution is a tool for each output that the two nested summation is needed and multiple, and but the multi-channel convolution, for each output, the 3 nested summation is required, and this for this output data is a three-dimensional tensor, and so in a simple implementation of this formula, it requires a 6 nested loop programs. And this shows what is a software history array means. Software history array-based model-based computation means, and the SSM-based method is a stationary approach. This means that stationary means the input image and filters are scaled to the thread during computation and does not transfer to the other threads. And but the data persistic movement is performed on the partial sums, and the partial sums are transferred to the neighbor threads. And this SSM-based input station approach realizes the cyclic data movement by using the CUDA shuffle primitives, special CUDA instruction to transfer data to the neighbor threads. And in this implementation, use this method to transfer partial sum to the neighbor threads. And the other notable fact of this implementation is that all data of filters are stored into shared memory in the beginning of CUDA kernel and reused during the convolution computing. And the other thing is that the input image data are charged into registers. We have designed two kinds of multi-channel methods based on the single input, single output software history array model-based convolution. And we call the first method out-in, and the second we call the second method in-out. And the out-in method performs the MIMO conversion by iterating a multi-input single output conversion across multiple output channels. And the in-out method performs the MIMO conversion by iterating a single input output conversion across multiple input channels. And this shows the pseudocode of the out-in convolution kernel with C input and K output channels. And this in the program that the details of this program is in our paper, and the loop related to the output channels is in the outermost loop, and on each iteration of the outermost loop, the input single output convolution is conducted, and partial sums is transferred to the neighbor threads by using this shuffle primitive instructions like this. And this is in-out conversion, the other method, and this is in this program that loop related to the input channels is in the outermost loop. And the other notable fact is that in this implementation, the array for keeping sums is initialized to 0 in the before the loop, and after the loop, the array of sum is returned to the memory, and this is a number of required operations and memory accesses of the two methods, and the required floating point operations pass rate and the output amount to the GPU memory, GPU DRAM memory is for both methods are same number of floating point operations and the output amounts, but the input amount is different between the two methods, and in-out method in ideal case, in-out method requires k times less memory accesses than out-in method, but this in-out method requires k times larger temporal data has to be kept in registers. So this in actual implementation, that this larger temporal data is not so good for the high performance. So as I will show you in the following slides. And we evaluate our implementation on our GPU, NVIDIA GPU, GeForce RTX 3090 of Ampere GPU architecture. This GPU has 10,000 CUDA cores, about 10,000 CUDA cores, and peak theoretical single precision performance is about 29 teraflops. And in this research, in the study that we show the performance in terms of gigaflops, floating point operations per second, and the gigaflops performance is calculated by number of operations divided by computation time. This shows the performance of convolution computing with C input and K output channels for H by double image. And this whole figure shows the different conditions, and the left one shows the case of the number of output channel is 1 case, and the right one is the number of input channel is 1. And in each figure, that the horizontal axis represents the filter size, and the vertical axis is gigaflops performance, and so the higher is better. And this red line shows the performance of outlying method with 8 input channels and 1 single output channel, and the blue one is the performance of in-out method and with the same number of channels. And as you can see that this red line is better, and so out-in method is iterations of MISO method is faster than in-out and OGR method. And for example, in one case, that the out-in is 1.14 times faster than in-out method, and about 6 times faster than the original single input, single output channel implementation. And we have conducted to see the performance to see the reason of the performance tendency. We have profiled our implementation and by the NVIDIA Insight Compute Profiler, and this table shows the profiling results, and some of the results and the charge hit rate and the instruction issue slot utilization are shown. And in case of k equal 8 case, that the outwin shows a higher charge hit rates and a higher instruction issue slot utilization than the other methods. And the memory utilization, but the memory utilization of in-out is not efficient, like this case, blue box case, that many memory access is counted and memory, and this is probably caused by register space, means that not enough number of registers cannot allocate at once, so many and register space, which leads to repeated read-write accesses between the registers and of chip memories. And this is another result, and the performance of convolution computing by out-in method with C input and K output channels. And and the four linear showed, I put the four results with different sizes of images, and in this, in each linear, the horizontal axis represents the input channels, and in this linear, we also show the performance of the QDN, and the gray line shows that it's the QDN's performance, and but this QDN is not so good for on this condition, and maybe data alignment is not good for QDN, and the implementation of our implementation shows a higher performance than QDN, and the more detailed comparison with other existing library is in our future work, and the other important factor is that increasing the number of channels improves the performance of relatively small image sizes. So the performance increases by increasing the number of input channels, but does not always improve the performance, especially for large sizes. So 1024 case that the filter size is in some bigger filters input channel cases that the performance drops. The last two linear, and also in this case that we also profile our implementation. This is a profiling result on the charge hit rates of the art in convolution for 3x3 filters. And the left one is left two linears are A1 charge hit rates, and right two linears and two charge hit rates. And A1 charge hit rate for 128 by 128 images does not drop down even when number of input channels increases. But for large cases that A1 charge hit rate decrease and leveled off along with increasing number of channels. And so this tendency is confirms the previous performance results. Okay, I'd like to conclude this presentation. We have developed a high performance kernel for multi-channel convolution with a stochastic array model by extending a single channel convolution kernel. And the performance is higher than the single channel kernel on a GPU. And the profiling results show that the efficient usage of registers and caches is more important for the multi-channel computing than the single channel computing. Okay. This is all for my presentation. Thank you for your kind attention.
Thank you, Matsumoto. And there's any question? So, if there are no any question, I say thank you already.
Okay.
And if you want to stay with us, we continue with the next presentation. With the presentation of Garima Singh is there.